So thank you, Alejandra. So yeah, this is a notebook. I will put it in full screen. So as I was saying, we will access some Supernova through the API, which is a recommended way to access the data. But if you have more sophisticated queries, we will do a direct database connection, which in many cases is what you end up doing. But to start, it's good to learn to use the API. So this is based, of course, in the work that we have been doing for a long time, and that is shown in these 3 papers. So if you have more questions, you can go to these papers, or also you can contact us. Okay, so some warnings. The database that we are using, that you will use in this tutorial, is not yet in production. That means we cannot access alerts from last night. Alerts from last night are currently in the production mode database and in the production mode API, but we wanted to show you the new API because it's a new database, because they are much richer and you can do more fun things. But they will be in production mode in a few weeks from now. There are some things that we need to fix in this database, but there are details that you can read here. So we will start by pip installing the new ALeRCE client, this command. So you will get this warning message because I opened this straight from GitHub, and you just do run anyway. So this is starting from like a clean installation of a clean session of Google Colab. So now this will run, and it's installing the new pipeline, the new API, and the client, sorry. And there it is. And if it's correctly installed, you can load our libraries, our client, and we can initialize it in this line. Okay, so now we have the client. We will also load other libraries. So some basic pandas, matplotlib, numpy, and some astropy. For example, things related to cosmology that will allow us to compute distances. We will also load AstroQuery to query the net and some dust map APIs here. So the good thing about Colab is that, of course, you can run in the cloud, but you have to install the libraries that that will not come by default every time. But that's not such a big problem. And then some other things related to some embedded Aladdin images that we will show. Also, I will define some colors because we have found this colorblind friendly green and red for the green, G and R band. So we are trying to use this every time we can. Okay, so first, I will create a simple function to plot a light curve. So this is the object, and I want to show you. Let's see if I can get into the new Explorer. I want to show you here the light curve first. So I put the object, search, and there it is. And here is the object. So it's a supernova, a type 1a supernova according to the classifier. And this looks correct because here's a type 1a supernova, and because it has a secondary maximum in the R band. This is the galaxy, the host galaxy. You can see the image stamps. So yeah, so just play with this candidate first. And I want to show you how to access to this data programmatically. So first thing, I will define a function to plot the light curve given an object ID and some data frames. So yesterday, Camilo gave a very nice tutorial on pandas. So in this function, I will create uses as input 2 data frames, the detections and the non-detections. Okay, and I will use some labels. Filter ID of 1 is equal to G. Filter ID of 2 is equal to R. Markers, I will use circles and squares and different sizes. And basically what I will do is to first loop through the two bands and create a mask asking for all the detections that match the given band. And if there is a detection, plot an error bar, do an error bar plot with the MAC PSF as magnitude. This is a magnitude associated to the image difference, and sigma PSF, which is the error associated to that magnitude. Okay, and then I will do something similar with the non-detections, but in this case I will use markers like arrows, indicating that there's a non-detection up to that magnitude. Okay, so this is the function, and then I will create a function to get the data using the API. So this is the key line. In here, so the nice thing about Colab is that you get these windows and it shows you something about the options. So the options are of query detections for a given object ID. And you can see that you can get it in different formats, in pandas format, in biotable, in JSON. So we are using pandas because it's so easy to use. And then I will sort the values by MJD. And I will save it in a dictionary, saying that these are the detections of the given light curve. And I will do something similar for the non-detections. So here they are, and here it is. And then if I ask for a plot to mate, I use the function that I just defined before. Okay, so very simple functions. And here's the result. It will do all this query through the API. Oops, I didn't define. There it is. I didn't define. Yeah, I have to do this. Sorry. Yes. Now the three functions are defined. I hope. Just do this just in case. And run it. Yeah, and here it is. So it's the same light curve that I showed you before. This one, but here you can see all the other information that is very nice to see. And by the way, you can also see whether this object is known in TNS, and actually it is known. It's a type 1 supernova with this name and it has a redshift of 0.0493. Okay, so moving forward, we will do more advanced plotting now. So one thing I will do is to try to do extinction corrections and also distance correction. So I will modify my plot function, and I will give two more parameters: the vector of attenuations and a given redshift. Okay. So by default these are known, but if the function finds that they're not known, then it will do something. Okay. So again, I will do the same thing. I will loop through the two bands, and if there is an attenuation vector, it will get the given attenuation in the given band, and then it will do the same as before, but it will do two things. It will correct by the distance modulus, because we computed here using AstroPy with the given cosmology for the given redshift, and also will correct for the extinction. Okay, so these are the two options. And yeah, that's it. And then I will do more complicated labels because we have so many options now. But this is the basic idea. Okay, so we'll get the data, and now we do something more complicated than before. We don't only use the API for the detections and non-detections. We will also query some basic statistics. So you use the query option function of the client, query detections and query non-detections. And for example, with the basic statistics, we can get the coordinates. We have a column called mean right ascension and mean declination. Why we use the mean? Because there actually each object has many independent associated coordinates in the sky, and we use the mean. With this, we can create a sky coordinates object from AstroPy that we can use to query an external service for the attenuation. Okay, So this is something that normally you will do manually and like with lots of will take a lot of time, but this is all done automatically. And also we can actually even go and get the galaxy. So in here we will query in net whether there is a galaxy or some object. So net is the NASA extragalactic database, and we use the coordinates again in a very small radius, and we get the redshift if it's available. So with this, we transform this VO table object to pandas, and then we say whether the redshift is not none. Where the redshift is not none, I will get a redshift. And then finally I can plot, and I can give the attenuation and the redshift. And I will display even the link. I will modify here to show you the same link as before. And I will plot the stamps as well. So here I'm using another time the client. I will use the function get stamps. So for get stamps, I need the object ID and the candidate ID. So every object has a unique identifier, which is the object ID, and every detection of a given object has a unique identifier, which is called the candidate ID. Okay, so what I do first is to get all the detections that have associated stamps, and I get the minimum candidate ID. So this is all what this line means. And then I get three images: science, reference, and difference, and I will show them here. So you see all these things I'm doing in just one function. This is the nice thing about APIs. Let's see if this works. So okay, it asks net for objects. We found several objects, and in particular one had redshift, and we will assume that this is the redshift. So in this case, we got the object corrected by the attenuation, so it went up a little bit, right? And then also the absolute magnitude using the distance modulus of the given redshift, which is shown here. Okay, so we have two versions of the same. This is the apparent magnitude corrected by attenuation, and this is the absolute magnitude, also corrected by attenuation. And here, of course, there's some caveat that we're not doing K corrections. That means the spectra of the supernova is redshifted by the distance, and this will change a little bit the proportion of flux in the two bands. But given the very low redshift, this is probably not so important. And here you can see the image stamps. And here you can see, for example, that this supernova is a type 1a supernova, and the peak is around minus 19, which is exactly where type 1a supernova are supposed to be. So here you have a function that you can use for your science, for any extragalactic object, and we'll give you all this in just one line. So now I move to some other object, one of our favorite objects that Ignacio also showed yesterday, CTF20 AAE Lulu, also has a nice name. And let's see. Okay, found many objects. In particular, there was one with redshift, which was very nearby, 0.072, and also gave me a link. Let's go to the link. I'll show you this object in more detail. Here it is. And look at this beautiful galaxy. So this was a very, very nearby supernova that we discovered with just one detection here. And we got a spectra between here and this second detection. So this was like the dream that we want to achieve, but we want to do it faster. And here you can see all the detections. Also, you saw some yesterday with Ignacio, and the probabilities. In this case, I will classify this as a type 1 BC, either of those. And actually, TNS confirmed that this spectroscopically, this was a type 1C. It's a very nearby and young type 1C. Okay. Okay, so again, you have the apparent magnitude and the absolute magnitude. Okay, how am I doing with the time? Let's see. Yeah. Okay, so after this, I will show you some cool example of how to get the Aladdin image in the notebook. So something we could not get to work in Colab is using the library called ALeRCE, which is a really, really cool library that allows you to interact with ALeRCE images and catalogs. But the simple option that we managed to make work in Colab is just embed ALeRCE Lite. And here you can see the galaxy on your notebook. So if you try, I really recommend you to go and try ALeRCE library. Okay, so this was for individual objects. So let's move to more objects. Yeah. Okay, so first thing, when we will query many objects, we will query objects or different classes based on their probabilities. So for this, then it's important to understand that we have a taxonomy that is limited. Right? It's, of course, cannot include all the classes in the universe. We just include the most important or the ones that we have good training sets. And in particular, we have two classifiers, a stamp-based classifier and a Litecoin-based classifier with two different taxonomies. The more complex taxonomy that includes subtypes of supernova is this one, and a very simple taxonomy that includes only supernova as a general class, which is really extragalactic and is included in this stamp classifier. So here are the classes. For the stamp classifier, you have AGN, supernova, variable star, asteroid, Bogus. And for the late classifier, the Litecoin classifier, you have type 1A, type 1B or C, type 2, superluminous, supernova. Okay, so only 4 classes in the transient branch. The idea is that we will continue improving this, but we need more data, better models, etc. Yeah, so someone asking if I could add an example of using iPiloting on the Colab notebook. Yes, I could do it after finishing, just the code, and so you see that how to use it in your own laptop. This is the confusion matrix of the Litecoin classifier, and so you see that the supernova branch is the less precise of all, and this is because there are fewer examples than of the other classes. So this is more difficult to train. So we are really working on getting this better by using data augmentation, so creating more data from the data, and also models, synthetic models. You can see also in Paula's paper, the recall, so this is a fraction of supernova that you recover as a function of magnitude, and you can see it's actually quite good. We really get most of the supernova when they have G and R band, when they have G, or when they have R band. Okay. Okay, so now we will do the query. We will query the top 1,000 supernova that exploded at least 70 days after the beginning of CDF. I don't want to have problems with the reference image. And I have a probability of greater than 0.4. And also that are assigned as type 1As and that have between 10 and 50 detections. So I'm asking for a lot of constraints here. And I will ask the Litecoin classifier and the supernova 1A class name. I will order results by probability in descending order. And here you can see the first MJD is limited between this first MJD and nothing. Okay, so here I will do the query using the client again. And let's see what we get. Okay, so we got 733 candidates with 23 columns that you can see some of them here. Okay. So the most important ones, number of detections, the color at maximum, the mean color, the first and last time, the length of the light curve. This could be important if you want to filter. Coordinates, the error in the coordinates, the class, the classifier, the probability, and the version of the classifier. This is also important for in the future because we will have different classifiers. Okay, so I will show you all the column names here. Here you can see again. And we will do some simple plot. First, just show me all the colors at maximum. So I use this data frame, which we call supernova. Also know that I made the object ID as the index. So this is what you see here in bold. So this is the index. And calling the Supernova data frame dot g minus r maximum in 50 bins, I get this. And this is more or less what you expect. The color of g minus r of type 1a supernova maximum is around 0. Let's also look at the number of detections. I'll do it in a different way using the pandas histogram plot function. And here you can see the number of detections. And now I will do I will use the previous function that I built before for a random selection for 5 randomly selected supernova from this 733. So I will do everything, all the light curve, the redshift, etc. So let's see what we get. So first was this one, and the second one. First querying all this, and then we'll show all the images. This is the way Colab works. So here are the candidates. This one was not very well observed, but it looks like it's near a galaxy. This one was much better. You have extinction correction, attenuation, but there is, you couldn't find the redshift automatically. You can see the galaxy here. Same here. This is also type 1a. Yes, again, another one was not super well observed. So with this, you get an idea of the kind of objects that we get that are coming in CDF. There are very good well observed objects, and some that are not so well observed. And another one, yeah, and in this case, you can not really see if there was a galaxy. This could be a misclassification. I don't know. And in none of these, there was a galaxy in net. So this is the most common thing, that you don't find a galaxy in net. If you want to find the redshift, you will need to query Sloan or some more advanced database that has automatic redshifts, etc. So I recommend you to try that. Okay. So now we will do the most fun part, doing direct database connection. Okay. So this will be not so simple as before, but just as an introduction, remember that our database has many tables. Some of the most important are the object table, which is basically aggregated by object. So only properties that are aggregated of properties of an object. The probability table that contains all the classification probabilities. So each object will appear many, many times in this table. It will appear in as many classifiers times classes there are. So we have one classifier with 5 classes and another classifier with 15 classes. That means a given object will appear 20 times with a column that will tell you which classifier is referring to and which class is referring to. Then magnitude statistics, is a table of magnitude aggregated per band. Okay, so a given object will appear if there are 2 bands, G and R, 2 times. Then we have a PS1 CDF table, which has the closest band stars matches. And then we have detections. These are the light curves. Okay, this is the raw data, let's say. And then we have features. Features are characteristics that we extract from the light curve. By the way, I don't think I will finish this notebook, but I just want to go through this part first. Okay, so for this, we need to load this library to connect to the database. And we will load the credentials that are public. You can see it in our GitHub using this line. And here we will open the connection. So we will use the credentials that were loaded here, database name, user, host, password, and we will open the connection. And now we are connected directly to the database of ALeRCE. The first thing I will do is to show you all the tables that are available. Someone asked this yesterday. So here you can see with this command, I can query the PG tables table and see exactly what are the tables at this moment. And here you can see actually more tables than the ones that I referred to before. Okay, so here's another description of the tables. And now I will query all the columns of a given table. Okay, so I'll do this. This will give lots of information. And here it is. So you can explore all the different tables and all the columns. So for example, here's the object table. You can see all the columns. You can see probability. That's all the columns: classifier name, classifier version, class name, probability, and ranking. Ranking means is it the most likely or the second most likely, etc. And now we will do the first query. And for this, I want you to stop and look at this more carefully, because this is not a simple query. So what we want here is basically all the objects that are classified as type 1A, 1BC, supernova type 2, or superluminous supernova that have a ranking of 1, that means they were the most likely class, and that have a probability, so that the most likely class with a probability of greater than 0.2. Okay, so why I do this? Because if, for example, you have all the probabilities being the same, but very low, ranking equal 1 will be associated to all of them. So this is important. So I go from the bottom to the top. So it's a bit, you have to think backwards a little bit when you do these queries. So there is this table that selects objects with these constraints. And then we want the following columns. From the object table, all these columns, and from the probability table, all these columns. And because I'm asking columns from 2 different tables, I need to do a kind of join. In this case, we'll do an inner join between object and probability tables, saying that the join can be made through the object ID index. And we'll say where the classifier name is LightCurve classifier, and the object ID is in this list of object IDs. Okay? So I want you to think about it, a little bit about it. And if you have questions, please, this is a good moment to ask. So again, I'm asking columns from 2 tables that I join through this inner join, and I'm putting conditions. And the important condition here is that the object ID needs to be in this selection. So this is the way we are going to select. So when you use API, you don't have to worry about all this select and where and from, inner join, etc. But the possibilities are not as complex as this. You have fewer possibilities. So let's try this. There's a question here. Would you recommend any book on SQL? Actually, I've learned most of it through tutorials in the internet, but if someone else in the team has a good recommendation, but that's not a silly question, that's a good question.
Yeah, I think we have to check that. I don't remember any book from SQL right now, but we can send you an email if you want.
Thank you, Gavin. Okay, so I did this query, and now I got...
We have 10 minutes.
Okay, thank you. So we got 97,000 results. So, and we got all these columns, which are the ones we asked for. The position, the number of detections, the time of first detection, the duration of the light curve, the color at maximum, the classifier name, the class name. Yes, so someone is asking if there are more query examples. Yes, there are many notebooks with many queries, but if you have some that you would like, you can ask us. And here you can see, for example, that in this case, I see only the same object all the time. And this is because I can see all the light curve, I mean, all the classes, sorry, probabilities for this object. That's why the object appears many times. Okay, so we will look at the first appearance. So we'll get the first index and show only those indices. And this is the first object. So what you can see here is that this object appears 15 times. I know the number because I know that these are the number of classes we have. Okay, and you can see the ranking. So this object has most likely type 1A supernova, then type 1BC, then type 2, and then superluminous supernova. So all in the Supernova branch, and these are the probabilities. Okay, and one thing we would like to do is to move these probabilities in these class names into columns. We want to do some kind of transpose of this matrix. And for this, you can use the pivot function, which is a great function in pandas. So it's as simple as this. Just do pivot with the column class name, and voila, you have one object per line and all the columns in here. Okay. Okay. So now that we have this pivoted data frame, we can do very simple queries. For example, I get the probability for type 1 BC and the ranking for type 1 BC of this object. And here it is. The probability and the ranking. And let's look at the probabilities for type 2 supernova. So I say show me only the type 2 supernova, so that means ranking equal 1, and show me the probabilities, the distribution. So because I put a cut on 0.2, remember at the beginning, I get this distribution. So the most likely type 2 supernova in this case are 0.5 or something like that. So as you can see, the classifier is not really certain. The probabilities tend to be low for the supernova class. Now we will do something different. We will plot for all the objects that are classified as type 2 supernova with the first or most likely value, so the ranking equal 1 or 2, and we will show the probabilities of being type 2 versus type 1a. So again, this is the probability of being type 2 supernova, this is the probability of being type 1a supernova, and these are all supernova that were classified as supernova type 2, either first or second probability. And you can see one thing you can see here is that the frontier between these two classes is not very well separated. So this classification is difficult sometimes because you actually don't have many points, or they're very noisy. So there's some confusion with type 1a supernova, and this is confirmed if you look at the confusion matrix. And for example, the things that are classified as that are really type 2 supernova, a significant fraction are actually classified as type 1a. Okay, so this is something that we are working really hard to make it much better, and I'm sure this will happen because there are so many new techniques in machine learning that we are testing. Okay, so I will do something similar for type 2 versus type 1 BC. So there is not as much confusion between type 2 and type 1 BC. You can see here. And now we will compare the length of the light curves of objects that are classified as type 1a or type 2. Let's look at this. And something you see clearly is that type 1a supernova light curves are shorter, which makes sense. This is what we know. Type 2 have this plateau light curve. Type 1a have only the radioactive diffusion peak that tends to be much shorter than the plateau of type 2 supernova. So this makes complete sense. However, you see here there are some objects that are very, very long, and these are probably misclassifications. Okay, so let's do some quick, cool tests here on using the new table that we have, which is called magnitude statistics. And in particular, so let's find all the things that have a ranking of 1 in the previous table. Okay. And here we go. We select all the columns of MaxStat. Here you can see them. And in particular, there's a new column that I really like, which is this DMDD of the first detection. So what this means is if I have a non-detection before the first detection, I can compute some kind of slope, and I can constrain the rise time of the supernova. So here you can see that this object was rising at least at 1.2 magnitudes per day at the detection. And you can see here all the columns. And for example, I will show you the minimum magnitude of all this supernova. You can see there's some clearly a correlation between the minimum in G and R band. And I'll here plot all the supernova that are found rising, that you can put a constraint that says this is rising. That rising means DMDT is less than 1, less than 0, sorry. And also I ask for the time between the first detection and the last non-detection being greater than 0.5. Because if you have a very short DT between this D and DT, this can explode and can give you nonsense. So here it is. And you see distribution, there are some that are rising super fast at -4, -5 magnitudes per day. So let's look at them. Let's look at the fastest riser in this sample, which have a decent probability. Yeah, this is not this is old. Sorry. And here there, I put the links. So in this case, you have a DMDT of -1.5. Let's see. Let's see what we get. And yes, we get a very fast rise here. You see, there was this non-detection here on February 20, and then on February 21, we have something that is almost 1.5 magnitudes brighter. So this was really catch very young. Let's look at another one. Again, super nice rise time of this supernova, and you get the idea. So this table is really
on time.
I'm on time?
Yeah.
Okay, so I think we can leave it here, but I recommend you to follow the notebook. I didn't want to go very fast because you will not get much from that. But some quick interesting thing about I want you to look is the feature table. We actually fit a model to every object in CDF. We fit this model, and this is really powerful to characterize supernova. So I really recommend you to, if you're a supernova person, I recommend you to look into that. There is also some analysis of the host galaxies, something about the light curves, detections, and that's it. So, for example, these are the model light curve for all the supernova that were classified as type 1A supernova with large probability. So, yeah. So, and here there's some analysis of non-detections. And you can see, for example, that non-detections tend to really be mostly between 20 and 21. And if you plot them against the moon phase, you see that when there is a full moon, the limiting magnitude goes to 19 or something. So if you have any questions, please let me know.
Yeah, so we have 15-minute break right now. Then we will start with the viral start tutorial. I think we can answer some questions in this break, but if you want to go right now, you can go. Thank you.
Thank you. If there are no questions, I will pause the recording. Oh, what do you think is the most promising path to improve the supernova classification within ALeRCE? That's a good question. So there's something called the plastic challenge, where the LSST prepared a large set of synthetic light curves and set a challenge with a price of, I don't know, $20,000 or something to classify them. And there was a competition where people from all fields participated. And the winner in this challenge was actually one astronomer from Berkeley, a student that where his strategy was to use Gaussian processes to create new supernova from the data, to do data augmentation. So that's also something that we are trying. So that's the data augmentation strategy is very powerful. There are many ways. One is the Gaussian process. And also the other strategy is using synthetic light curves and plus fine tuning. So you train your classifier with synthetic light curves, and then you add some real examples and fix the parameters of your model a little bit from what you had before. And so I think these two strategies are the most promising. You can also follow the strategy of waiting for more supernova and getting more spectroscopically confirmed supernova, but this is really slow path to improving the classifier. But if you have any ideas, we are also happy to hear, and if you want to collaborate on this, we are also happy.